Today we're going to change the focus of these lectures. So far I've been focusing mostly on showing you how you can make Python do the kind of things that you usually do with spreadsheets, with manual processing and so on. So our focus has been on looking at tools that allow you to automate the same tasks that you are probably already doing, depending on the kind of work that you are doing. Maybe you'll find pandas more useful, or NumPy, you'll do some plots and things like that. But basically, we've been covering the same kind of things that you could theoretically do with spreadsheets, only the goal is to automate them. In these last 2 weeks, I'm going to shift to showing you some things that you can do that go beyond what you can do manually. So today we're going to start by looking at modeling with SciPy and modeling mostly dynamic systems. So basically systems that can be described with ordinary differential equations. I'm going to give the example of this epidemiological model, the SIR model, and chemical reactions. But the idea is to show you how you can model these dynamic systems using these differential equations. So, and also I'm going to show you how you can adjust parameters to some data. So this will be just a simple example, but the idea here is to show you how you can do this, which in general would be not very practical to do with spreadsheets. Now, these kind of examples are not probably useful for all of you right now, or maybe just for a few of you. But since we're going to start dedicating these last 2 weeks to the final assignment, I'm also going to take advantage of that time to show you some things that you can do that go beyond simply automating the tasks that you are already doing. Okay, so let's start by looking at the numerical integration. So to solve these kinds of differential equations that we can use to model dynamic systems. So usually if we have something that changes over time, it's very simple to model it using differential equations, and then we need to have some way of solving these equations. So the basic idea, the algorithms are actually quite sophisticated, but the basic idea is that if we want to compute the integral of a function, then we can just add the slices, some rectangles indicating the area beneath each region of the function. So this is a general idea. This is not the actual algorithm, because this would be a very simple version, but it's a general idea of how we can integrate numerically, compute the integral of a function. Now, if we have a function that is varying over time and we need to accumulate all the values, for example, with this model, then we have some more sophisticated methods, but the idea is basically the same. So let's consider this model here. This is a model with 3 compartments to model infectious diseases, where we have people that are susceptible to the disease. They can catch the disease. Those that are already infected, and so they can transmit the disease to others. And those that have been removed, either because they died or they recovered and now are immune to the disease. So these are the S, I, and R compartments. And we can describe how we expect them to change over time by writing the differential equation. So S, the number of susceptible people, will change over time as a function of the number of those that are infected and those that are susceptible. Because the more infected people we have, the more people will become infected by transmission, by contagions. And also, the more susceptible people we have, the greater the number of contacts with susceptible people, so the more will become infected. So as a proportion of the number of infected and susceptible, we will reduce the number of susceptible because they become infected. So there is this minus sign here, and we have this beta parameter that allows us to calibrate this. So basically, beta will be a measure of how quickly the infection is spreading, or how easily it spreads. So B is proportional to that basic reproduction number of the infection. So, and this N is a scaling factor for the total size of the population. Now we have the same thing for those infected. So those the infected ones are increasing at the same rate as the susceptible are decreasing, because the susceptible subjects will become infected. So we have the same term here, but now it's a positive sign because it increases the number of infected. But then we also have people recovering. And the number of people that recover is simply one constant that will be 1 over the average time it takes to recover, multiplied by the number of infected we have at that particular time. So at each instant, we have new infected people coming in. That depends on the number of susceptible and infected, and we have infected people going out, so into the recovered or the removed compartment, because they either die or they recover from the disease. And finally, we have the removed that are going to increase at a rate that is the same as the rate that the infected ones are being lost here. Okay, so this is easy to write how things are changing over time in this model, but now we need to compute how many of each type we have at each instant, and that requires integrating the function over time. So one simple way of imagining this would be an extension of this method, taking slice by slice, and this is basically Euler's method. We can assume that we take a small step of time, small enough, so a tiny delta that is sufficiently small that we can consider that during that time period, these derivatives do not change significantly. So they are approximately constant. In that case, we can compute the values for the next time step, starting from the values at this time step, and then just give a small fraction of the derivative at this time step. So these functions that we have here. So we just multiply by a small step and we go to the next value. There are more sophisticated methods. For example, we can do this backwards by solving for what the value should be after the time step, and this increases stability. There are other methods here. So basically, there are the actual methods that are used to compute this are a lot more sophisticated than the simple Euler's method. But we are not going to worry too much about that, because we have those methods in the libraries that we're going to use. So in this case, to integrate these differential equations, we're going to use the solver to integrate ordinary differential equations in the integrate module of SciPy. So basically, we give as an argument to this function the function that computes the derivatives, and then the int function will compute the integral of those. This by default uses this solver. You can look up the literature if you need more details, but we are not going to worry too much about that. We're just going to see how we can implement that and use that library. So we're going to import from the integrate module. We're going to import the solver. We're also going to import NumPy and Matplotlib to do the plots and basic computations. And I'm going to set this style for the plots because I like it better than the default one. And now what we need to do is to write the function that will receive the values at time t and gives us the derivatives at time t. So the values will be these, the SIR values at time t. It also receives the time and additional arguments that we want to give it. In this case, we don't need the time itself, we only need the values. And now we write the derivatives as a function of the values at time t. So basically, these equations, if we know how many infected, susceptible, and removed we have at a given time, we can compute how much these are changing per time unit at that instant, so the derivatives. And that's what we're going to compute here. These are the three expressions that we saw previously for the variation of the susceptible, the infected, and the removed. And now we return this as a tuple, the three derivatives. So this is what we need to write, the function for the derivatives. And now we can call the solver, the ODINT function, where we say which function we are going to use for the derivatives. So it's this one here for the gradients. We are going to give a starting value. So this starting value, when we create this function to compute the curves for this model, we can receive as a default 1 person infected, 0 recovered or removed, and a total population size of 10 million. So this will be the starting point. We start with 1 person infected. Now the starting point then, computing the SIR values, will be the total number of people minus the ones that start infected and removed. So by default it's 1 and 0. And then the I will be the initial value of infected, so by default 1, and R the initial value for removed. And now we have these two parameters, beta and gamma, that are the parameters here of the model. So these values here, beta determines how fast the disease is spreading, and gamma how quickly people are recovering. So now we just call the ODINT function, tell it to integrate this gradient function here, starting from these values. So these will be the values at time 0. We give it a vector of time values for it to compute. So these are the time values where we want the integral to be computed, and as arguments for our gradient function. So the additional arguments will be the n, beta, and gamma, so these three here, so that we can compute the derivatives. And now we return the solution of this integration, which is an array, that a matrix that has for each row the values of the integral of these parameters here, the SIR, and each row corresponds to the time step that we asked for. So we're going to create here, let's say that we are using time units in weeks. We're going to create 1000 points spread out between week 0 and week 52. We're going to use a gamma value of 1 over 2.5 because this is an estimate of 2.5 weeks for full recovery on average. So gamma is 1 over the time it takes to recover. And beta, so beta divided by gamma is the reproductive number. It's the average number of people each infected person will infect. So if we use 3 times gamma, then we are considering that the R0, the basic reproductive number for this disease, is 3. So these are the parameters. Of course, we can change the parameters. Now we call our function to compute. We get the matrix with the integral, and now we can do the plot. So basically, we can create an additional function to draw the plot with these parameters. If you are going to use representations on your on reports or things like that, it's very useful to create functions for plotting, because then you just call the function and the plot is always looks the same. So let's create a function where we specify the recover time. So this is the average time in weeks it takes to recover from the disease. We specify the R0, the basic reproductive number, and the file name where we want to export the plot. This is the number of weeks we want to run the simulation in, and now we can automate all of this. So the time steps that we want go from 0 to the number of weeks specified here, and we want 1000 points. This is so that the plot is smooth, the lines are well curved. The gamma value is 1 over the time it takes to recover from the disease. The beta value is the reproductive number times gamma. So these are characteristics of the model. We now compute the integral of this function. And here we can use this trick where instead of returning this matrix with 3 columns and 1 row per time step, we can transpose the matrix on returning, and now the matrix will have 3 rows and 1 column per time step. And since the NumPy matrices are indexed first by the rows, we can unpack this matrix into the 3 SIR vectors. So this will give us a vector of the number of susceptibles over time, the number of infected over time, and the number of removed over time. So this is not something that you need to do, but this is just to show you these kind of tricks that sometimes simplify the code that you're writing. So in this way, we now don't need to remember in which column the things appear here on the matrix. We can just use the SIR names because we unpacked everything into these variables. Okay, so now we create a figure. We plot each of these numbers, so the infected, removed, and susceptible. We're going to divide by 1 million, so we're going to use a scale in millions, and we can put it here in the Y label, people in millions, the X label is weeks, and we save the plot. So this is an example of what we get. Note that we are computing this integration for the first 52 weeks, so this would be 1 year, but we are asking for 1000 points within this range, because we want these lines to be smooth curves, not to be jagged. So if we were just asking for 1 time step per week, we would have some edges here. And this vector with 1000 points is what the ODINT function uses to determine which time steps for which time steps we want the integral to be computed. So it's going to give us as many values as those time steps for the different variables in our model. Okay, so this is one way we can do this. We can plot and just see the curves. So you see that we start with almost everyone in the susceptible container, or in the susceptible population. We have 1 infected, but since this scale is in millions, it takes a long time before we can see anything here. But suddenly things start to increase. So we have here the red line increasing with the number of infected people, but then people start recovering or dying and being removed from the equation here, which is the increase in green. So at some point we start decreasing the number of infected because we are decreasing the number of susceptible, and at some point we start losing more infected people than are appearing. So basically we have those things that we've been hearing about, herd immunity and so on, and at some point we no longer have infected people. Very few are susceptible, and most people now have been removed, hopefully recovered and become immune to the disease. Okay, we can improve this a bit. This is just to show you some things that you can do with plotting. This is what we already had. We do the plot, but now we can find the position of the peak by looking at the index of the vector I where the maximum is. So the peak will be the maximum of the number of infected people. And now we can check to see if it's more than 1 million or less. So if it's more than 1 million, we will put it in units of million people. If it's less than 1 million, we will write in thousands of people. And now we can create an annotation here by choosing a position for the arrow. So this will be the x value, which is so this is the size of the arrow that we want. It will be 1/10 of the x-axis here, and this 1/10 of the y-axis. So remember that we are using millions as units. So if we divide by 10 raised to the power of 7, this is 1/10 of the height of our graph. So this will be the size of this arrow here. And now we can create this annotation by using this text, putting this text in that position, and creating this arrow to unite the text with the peak. So basically doing this, so this is the text that we defined here, and then we write this arrow pointing at the peak. This is just one example, but to show you that with PyPlot you have a lot of flexibility with what you put on the plot. So it can take some work to fine-tune these positions, the annotations where you put the text and the arrows and so forth, but you have different options of writing the text, writing the arrows, and so you can, once you automate this, then your plots will consistently look the same way. So now we can add this legend here. To remove these white grid lines, I added this face color argument. So the face color is the background for the legend, where I get the color, the face color from the axis that I'm writing. So PLT is PyPlot, it's the module. GCA is get current axis, so it's going to get the current axis where we are plotting here. And get face color is going to get this background color for the axis. So if I want to create a box here that has the same color as the background, so as to overwrite the white lines that I have here in the grid lines, I can just get the color from the plot. So frame alpha tells me that I want it to be opaque and turn the frame on, so this background gets drawn here on the legend. Again, this is just a simple example, but it shows that you have lots of flexibilities to adjust the plots that you are making. And now we can save the figure. So here, this is an example using a recovery time of 2.5 weeks on average, and on average an R0 of 3, so the number of people each infected person infects. If we change these parameters, for example, we have a faster recovery time and a lower R0. For example, this was based more or less on what COVID-19 would be without special measures. These are approximately the parameters of the flu. So we have a lower infectiousness and also more quick recovery, about 3-4 days for recovery. So and as you can see, now we have a different progress of the disease, but we have the same plot again, and now the peak is marked this way because we automated all of this, putting the legend, the different colors, pointing at the peak, and so on. So now we can play around with the model and see the result. So this is an example of what you can do if you are modeling some dynamic system where you have differential equations. You can use odd-int, and then you can plot the result. And here are some examples of how to customize the plot. Note that these examples in particular are not very relevant. The important part here is for you to keep in mind that you have lots of flexibility to fine-tune your plots. And once you automate this, then it's very easy just to generate whatever plots you need, always with the same look and the same kind of information. Okay, let's look at another example where we have, in this case, we can have several concurrent processes. But I'm going to start with one where we are going to model the kinetics of some chemical reaction. But we're going to generalize this so we can write different reactions. For example, suppose that we have this reaction where we have two of some A compound reacting with B, and this with some kinetic constant that determines the velocity of the reaction will be transformed into C. So we can compute the forward rate of the reaction by multiplying the square of the concentration of A, because there are two A's participating, with the concentration of B raised to the power of 1, because there's only one B there. And this multiplied by the speed of the reaction in this direction, so this kinetic constant, will tell us how fast the reaction is proceeding in this direction. So this basically will allow us to compute the derivatives of these concentrations. So if we want to generalize, then we can generalize the derivatives for all of this, how we are going to compute, by starting to compute the rate of the reaction. And the rate of the reaction will be the forward rate, so this forward constant, multiplied by the concentrations of each of the species on the reactant side, each one raised to its stoichiometric parameter there. So if there are two A's, this is squared. If there is B, this is just B, or B raised to the power of 1, and so on. And when we have some reaction that is reversible, then we'll do the same thing going backwards. So using the products and the kinetic constant in the reverse direction. And now we can just compute the derivative for each species by multiplying the rate of the reaction by the stoichiometric coefficient for each of the species. If they are the reactants, then they are disappearing. We use a minus sign. If they are the products, then they are increasing. So this would be the overall expression. And now if we want to generalize this and model any chemical reaction, we need the concentrations for all the species. This will be the first argument for our function. We need the time we want to compute these derivatives in, the quantities in the reactions and the products, so all these stoichiometric coefficients, and the constants for the forward and reverse reaction. Okay, so this is just first we're going to use these parameters to compute the derivative, and if we have the concentration at time t, then knowing the stoichiometric coefficients and the reaction constants, forward and reverse, we can compute those derivatives. So the reaction rate will be the product of all the concentrations raised to the power of the reactants. Note that these are numpy arrays, so we are doing in one go this expression here. You see, we are going to raise the first one to its stoichiometric coefficient, the second one to its stoichiometric coefficient, and so on. So we can do this easily here in one instruction, because this vector has as many elements as the number of species we have in the solution, and this one also has as many elements as the number of species we have. So we have the stoichiometric coefficients for each of those species. And now we do this for the reactants. So we have the contribution in the forward direction, and we do the same thing for the products and we have the contribution in the backward direction. The difference between the two will be the overall rate of our reaction. And now the derivatives are simply the rate, which is a single value, multiplied by the coefficients for the product. So this tells us how much the products are increasing, minus the rate multiplied by the coefficients of the reactants, which tells us how much the reactants are being consumed. So this basically we need, I split the line here in two to make it simpler to understand, but basically this is 2 lines of code just to generalize this expression for any chemical reaction. And this gives us the derivatives at any time. We can test this. You should always test your code. One of the advantages of writing these small functions is that they are easy to test and you can check if they are working. So we can test with some simple examples. But then we can integrate the equation, these differential equations, to compute the concentrations over time of our species by creating again one vector with the times at which we want to compute this concentration. I'm using again 1000 points so that the plots are smooth, but this is a uniformly distributed set of values from 0 to the maximum time we want to simulate the reaction. And now what we're going to do is to call the function that solves these ordinary differential equations by giving the function for the derivatives, the one that we created here, and the initial concentration. So the initial concentrations are the starting point for our reaction, the vector of time values that we want, where we want these species concentrations to be computed, and the additional arguments that we need. So these arguments are the stoichiometric vectors for the reactants and the products. This specifies our reaction, and the two constants, the forward and the reverse constant. Now we can just create a function to help us plot. So we have the labels for the different species, the concentrations and the time. So these concentrations will be the result of our integration, and the file name if you want to save this figure. Note that I'm always doing this, saving the figure, because the idea here is not to run the code to look at the graphs, but to automate the generation of the graphs so that then you can import them into your documents, in your reports or things like that. So we are always aiming at automating these tasks. So we put the labels, time and concentration, the legend with the different names of our species, and again the same trick, and this is how things will look. So let's create a reaction that uses 2 of A plus 1 of B to generate C. So our initial concentration will be 1 of A, 0.5 of B, and 0 of C. These are arbitrary units, but we can imagine they are molar, for example. So we have 1 mole per liter of A, 0.5 of B, and 0 of C at the start. We set these two constants, so the forward constant will be 1 and the reverse constant will be 0.2. So this reaction is faster in this way. And now we specify the reaction. So the reactants are 2 of A, 1 of B, and 0 of C, because we have this reaction here. So this reaction has 2 of A, 1 of B, and 0 of C on this side, on the reactant side of the reaction. And this is what we specify here, 2, 1, 0. On the side of the product, we only have C. So we have 0 of A, 0 of B, and 1 of C. And this is the stoichiometric coefficients for the product. Now we simulate the reaction using these parameters, and we plot it here. So you can see that A is decreasing rapidly. B does not decrease as fast because 2 of A are consumed for each 1 of B, and we have C appearing here. And eventually this reaches an equilibrium where everything remains the same, because now we have a balance between the two half reactions, so the forward and the reverse reaction. One thing that you can do is when you have functions that have lots of arguments, you can call these arguments by name, and you can actually create a dictionary with all these different arguments for the different parameters, where you use the same names for the dictionary. So basically, we are creating here a dictionary from these variables, and now we can just provide these parameters as a dictionary. So we are giving the names, the keys of the dictionary serve as the names for the different parameters, and the values are associated, so they serve as the arguments that will be fed into the parameters. This can be done by using these two stars here. And so this is just a convenient trick. You don't need to know this to get this to work, because you can always call the function with all the different values that you have here. But you can use this trick by creating a dictionary with the different values, and then send that dictionary to your function. So there is a small typo here, so this should be like this. So these are the names of the functions. Oh, sorry. No, this is correct, because this is the way we are creating the dictionary. But I'll check with this. I think there may be something wrong with this line, but I'll check with this later. But the reason why this is practical is that then you can just change individual values in your dictionary. For example, the reverse constant here, kr, you can change it, and you can then send the whole dictionary again. So you don't need to be typing all of these different arguments. You use the dictionary where all the parameters are defined. You have arguments for all the different parameters, and you just change one that you want if you want to test different things. So in this case would be our original reaction with those speeds, but here we are changing the reverse, the constant for the reverse half reaction to 0, which means that now the reaction is irreversible. It's only proceeding forwards and not backwards. So now, instead of having this equilibrium here, we keep decreasing our reactants, A and B, and C keeps increasing. We can change, for example, now the speed. Let's change the forward reaction speed to 2. So now we have an irreversible reaction, but it proceeds faster, and we see a faster decrease in these. So this is for one reaction, but we can extend this to a set of reactions. So basically, we are solving a set of ordinary differential equations in parallel, but in this case, we can just do each one at the time, add all the contributions, and compute how much things will change for at each time step. So if we need to model several reactions, we need the reactants and the product, so the stoichiometric coefficients for all of them in matrices, where we're going to use one row for each reaction. And then we're going to need vectors for the constants, because now we have one constant for each reaction. However, the concentrations are the same for all reactions, because we have these species in solution. So in this case, we would have these 4 species, E, S, ES, and P. And we have 2 reactions. First, the enzyme attaching to the substrate and giving this complex of the enzyme with the substrate. And then the enzyme releasing itself from the substrate, but now we have the product being generated. So the enzyme catalyzed this transformation. And now we can model these two reactions, for example, like this. We can create the matrix for the reactants as considering these four species, so E, S, ES, and P, and the reactants of the first reaction are just E and S. There is no ES and no P on the first reaction on the reactant side. On the product side, for the first reaction, there is only ES, so this is the third one here. For the second reaction, which is this one here, we can model the part of the reactants by putting one ES here. This is the reactant. And then at the products, we have one of E and one of P. So we have here 1, 0, 0, 1, because the first one is E, this is S and ES, they are absent here, and then the last one is P. So in this way, by using these two matrices, we can specify both reactions. We now can create the arrays for the forward and the reverse constants. So this is the forward for the first reaction and the second reaction, 440. For the reverse, we have 150 for the reverse here, but then we have 0 for the second one. So the catalysis step we will assume to be irreversible. And now we can do a slight modification for the previous function. So instead of using that gradient function for the reaction, we can do this gradient for multiple reactions, where we start with an array of zeros for the derivative of all the different species. And now we're going to loop through all the reactions and add the derivative contributed by each reaction. So the idea here is that the way, for example, E is changing depends on this reaction here that is consuming E to generate ES, and this reaction here that is consuming ES and generating E again. So if we add the derivatives for the two reactions, we get the overall change of species E. And this we can easily do because we already have a function that we created previously, this one here, to give us the gradient, the derivatives for one single reaction. So now what we're going to do is to loop through all the reactions that we have and add to this vector that starts at 0 the contribution of each reaction. So what they contribute to, what each reaction contributes to the derivatives. And for this we're going to give the appropriate row of the reactants matrix, the appropriate row of the products matrix, and the value for the forward and reverse constants. And now we return these derivatives, which are the derivatives for all the species, but they aggregate, they add up all the contributions of all the reactions that we have. Okay, so now we can slightly modify the function to simulate the reaction. So this was the original function that we had that always used the reaction grad function. But now we can add an optional parameter where this gradient function will, by omission, if we don't specify anything, be the reaction grad. So this means that this function being called with only these parameters here will still use the original reaction grad function. So it will work as we originally implemented it. But we have the option of changing the function that computes the derivatives. And if we do that, it will use whatever function we give. So the reason why I'm showing you this is that sometimes when your programs start getting a bit more complex, you may find the need to update some functions in order to give them new functionality. So in this case, we want this function to work not only for a single reaction, but a system of several reactions. But at the same time, you don't want to break everything that was already working with your program. So it's useful to use these default arguments in your parameters that when the function is called without specifying a value for those parameters, it will still use the same thing that it was using originally. So in this case, it's using the original function for the derivatives. But if we want, we can specify a new one, and we can do that here by calling this function with the multigrad function for the derivatives. So this one that we created here. So again, we create an array, a dictionary, sorry, with the different parameters that we want, and we send everything into our simulate reaction function here. So this makes it easier to change things, experiment, and so on. And this time we are changing the derivatives function. We don't want to use the one by default, the one that just considers one single reaction. We want to use this one that considers multiple reactions. Okay, so now we create this dictionary, we send it to the simulate reaction, and you can see here the results of the plotting this model. So here you can see the products being generated, and then they are no longer created because the substrate is all consumed. The substrate is also being consumed here at the beginning, and here we have the two other species, which are the enzyme and the enzyme substrate complex, that are very low. We don't see them very well here on the graph, but what we can do is we can actually zoom in if you want to manipulate the scale and so on. I'll give an example a bit further on. We can zoom in here and see how these change. But we can complicate things a bit more. Let's consider that we have this reaction where the enzyme may form a complex with a substrate that then produces the product, but this complex may also interact with another substrate molecule and then produce a product, and again create this initial complex with only one substrate. So we can just extend the matrices here. I'm not going to detail each one of them, but basically each of these rows corresponds to one of these reactions here. We have now these 5 species, so E, ES, ESS, and ES, ES, ESS, and P. These are the 5 species, and you can specify all the different reactions, both on the size of the reactant and on the side of the products. We can also specify different constants for all of these reactions, and now we just run everything, and we have all the different complexes here. And if we want, we can just look, for example, at the enzyme and the complexes with the enzyme by from the results of the simulation, just taking the rows 0, the columns 0, 2, and 3, because this is the first species, the third and the fourth species. So we take just these columns, the appropriate labels, and this basically is zooming in on this very low region over here. So note the Y scale of the concentration. We are now between 0 and 0.05, but we can see what happens. We have this complex between the enzyme and 2 substrates that is dominating for most of the reaction, because we have lots of substrate. But when the substrate starts disappearing, then we start having more of this complex with only 1 substrate and increasingly less of the one with 2 substrates, and then we consume all the substrates and all of this disappears. And so the free enzyme is very rare here, but then at the end of the reaction we have the enzyme again free. So this is just an example of how you can complicate these things, and you can use this kind of differential equations to model dynamic systems that can be very complex. But then, as long as you have these sets of ordinary differential equations, you can either solve everything with ODE-int, or you can solve them partially outside. For example, in this case, we were adding the different derivatives, but the idea will be the same. And so this gives you a lot of flexibility to model dynamic systems. Now, another thing that we can do is we have a set of data points, and we want to adjust some model to that data. I'm going to give you just a very simple example using the data from the first days of the COVID-19 epidemic in Portugal. So this we have this table with the number of positive cases. So confirmados will be the positive cases here, and we can read this CSV file using pandas, and then just plot this column. So this is how the confirmed cases was increasing in the first 100 days of the epidemic here. We can select the initial exponential phase, so until we reach 5,000 cases. We can do that easily by, so we want between 10 and 5,000 cases. We can do it like this. We want from this column, so first from the data, we get the column of all the confirmed cases. This is a series. And now we get from this only those rows, so the items on this series that conform to this expression here. Note that we can use this ampersand to combine two Boolean arrays. This will be a conjunction of the Boolean values. This first one is a comparison between the number of confirmed subjects and 10. So it's true for all those that are greater or equal to 10. And this one is true for all those that are smaller or equal to 5,000. When we do the conjunction of these two, we get only those that are between 10 and 5,000. So this will extract from our data the column that we want and the values that we want in this range. Okay, so now if we plot this, we see that we have a fairly good exponential growth in this first stage, and we can now try to fit an exponential curve. There are many different ways of fitting models with SciPy. I'm just going to give you a simple example, but we can use this curve fit function, which basically takes a function, the x values, the y values, and some parameter that we can adjust. And now we call this function to adjust the parameter and give us the parameter. If you have more complex expressions, you can use things like minimize, also in SciPy and so on. So they are a bit more complicated to use, but you have lots of powerful tools there to do model fitting. This is just a very basic example. So now we can create a local function, because since this curve fit function does not give us the possibility of using additional values or sending additional values to our function, we have a difficulty in accessing this initial population parameter here. But basically our exponential curve will be the population at time t, so the number of infected people at time t, will be the population at time 0, the initial number of infected people, multiplied by some beta parameter, which tells us how the curve is shaped, raised to the power of t. So this is an exponential growth. So we can adjust this beta parameter. This is what curve fit will try to adjust by calling the function with the values x, so the values of these of the different days that we have here, and the parameter, compute the predicted values from the function, and compare those to the y and adjust the parameter to minimize the quadratic error. Now, since we need also our function to access this population 0, and we don't have a way of adding this as an argument, because if we added this as an argument, it would fail when curve fit tried to call our function. We can use a local function. So this is something that you can do. We create this function to fit the exponential. We have this target value here. These are the target is the actual number of infected people on each day. And we are going to start with the population 0 equal to the first value on our target array. So the first value for the infected population is the initial infected population. Now we're going to create this vector of time. So basically we are going to consider that the first day is day 0, then day 1, and so forth. And we will use the function curve fit to fit our exponential function at these times and try to approximate the target values, which are the actual number of infected people that we have in our data. Now, because this function needs to access the population 0, we can create it inside the fit exponential function. So note the indentation here. This function is a local function inside this larger function here. So this means that when Python is looking at this value here, pop0, it can use it from here because it looks outside the scope of the function. So this is one way you can go around the limitation of some of these functions in SciPy that do not allow you to add arbitrary arguments to the functions that you are creating. So this curve fit will now adjust the beta in order to make the result of this function here as close as possible to the actual values that we have. And now we can plot everything. So basically we're going to read the data, select the exponential part, this here, and fit the curve, computing the beta value. By the way, the curve fit function returns two values, the best value for the parameter, in this case the parameter beta, and a matrix with the covariances, or the value of the covariance for the fit, but we don't really care about that one here. So we are going to return this. This will be an array with all the different parameters that we are trying to adjust. So in this case, it's only one, it only has one element. And so we basically return just the beta value. And now we can use that to compute the actual curve of the fit, the fitted function. So we start with the initial number of infected people, and then we compute beta, that multiplied by beta raised to each value of x, where x is just our time axis. Okay, so now we plot the line and the data. This is the circles are the data points that we have, and this is the fitted exponential curve. And this is the beta value that we got here. Okay, so to sum up this part, this is something that if you are not working with dynamic systems, then at this moment it will not be very relevant for your work. But the main idea is to give you an example that goes beyond the kind of things that you can easily do with Excel, for example, or spreadsheets. So far we've been looking at how to automate things that you already can do without programming, but that usually are a bit boring and take some time. These 2 weeks now at the end, I'm going to show you things that go beyond that and that you really need programming to do. But if you can figure out how to do them and you practice a bit more, then you'll have more powerful tools at your disposal to solve more complex problems. So we saw how to use numerical integration to model these dynamic systems. A simple example of model fitting, so fitting the curve. I'm going to show you another simple example in the next lecture, but the idea is that you can use these tools to model, to fit the parameters of any model that you have to your data. And also we looked at some details on visualization, so different options for plotting, charts. Again, these are just examples to give you an idea of what you can do, not necessarily exactly like what I did, but if you need to create these plots, you can look up the documentation and you can really fine-tune a lot of details. So always remember that behind this is this goal of automation. So if you write a function to do the plot exactly the way that you want, even if that takes some time and some work to get everything perfect, once you have that, you can just reuse the function and do all your plots in the same way with no additional effort. And that is a very important goal here in this course, that you get used to working that way. Okay, so let's take a 10-minute break, and at 10 minutes past 6 I'll start the second lecture. See you soon.